where we need to understand that we study the conversions between the chemical energy to what? Chemical energy and vice versa to electrical energy. So what did we say? What cell converts from chemical to electrical?
Galvanic cell.
Okay, it's a galvanic cell. So what are some of the things that tells you to say the reaction was spontaneous? What are some of the indicators that you expect to have?
The standard cell potential is positive.
So by the way, just know that it's a galvanic cell where the reaction is spontaneous.
Negative.
So you're saying when the standard cell potential is what? Standard
Positive.
when it's positive. Okay, what else?
Gibbs free energy will be negative.
So negative standards Gibbs free energy. Okay, this is good. This is good. This is good. And one other thing that we had talked about was, of course, we do know the other cell that does the opposite is what? It's an electrolytic cell, right? Okay. When it stands spontaneous, then the opposites are true. Then we also talked about the next equation, which helps us to calculate the non-standard cell potential, right? And then this side we said it may be 0 point. In a case where it's 0.0 what? 592, it will be over what? N,
N
and it matches up to what?
log Q.
Okay, log Q, capital Q. Then at equilibrium we said this one is a 0. So the formula ultimately turns out to be your K, which is the same as your Q, is equivalent to what? Who can remember what we said?
10 to the power.
Okay, let me leave it this side. Log K.
The standard cell potential.
Cell potential.
Open brackets.
Open brackets.
N
N
divided by 0.
So
0.05.
in case you,
0.05.
okay, so this is very simple. It's just like you remove that guy there, take this on the other side, and then make Q the subject. Okay, that's when you're asked to find the K.
So,
That's
sir,
yes.
is it possible just to take ant log of K?
Yeah, if you do, that's what you're supposed to do. It's generally for you to basically get to find the exact value of K. Okay, on both sides.
Alright.
Then the other thing that we talked about is the aspect of you being able to calculate this from the same equation, the non-standard cell potential. We said you can calculate it using what? This value. So it requires you to use your Q now. So your Q, we said, it's basically going to be, look at the reactants that you have and your products that you have in a reaction also. So in this case, you only consider what is in aqueous state, right? Aqueous and gaseous, but you're not going to have gaseous here most of the time. So deal with aqueous, forget about the solids and the liquids. Just get what is in aqueous. So assuming I only have a single reactant that is in aqueous as my product to be on top, its concentration, of course, divided by the concentration of the other what? Reactant, which is B in aqueous as well. And these are supposed to be raised to their stoichiometric powers. So if C has got 3, for example, it's supposed to be raised to that power. That's what you said. So that you find your Q, you know your N, which is the number of electrons, your E standard, you know how to determine it from a galvanic cell, and then you'll be able to find your non-standard cell potential at 25 degrees Celsius. Okay. Just that was just a quick reminder. And so I know some of you were already requesting about asking about the videos that I told you I was going to work on, and I said I was going to work on the videos starting this Saturday because of exams this week. So I'm finishing on Friday. When I'm done with exams, that's when I will now get to make the video. So
So,
yes.
so this is my first time to attend chemistry class. So, did you do the same work done using that kind of Faraday's constant and the like? You find the work done using the number of moles
We said the work.
and the like.
We said the maximum work done is what? Okay, remember the number of moles multiplied by what? Okay, remember. Gibbs what?
And Gibbs.
Okay. This is what we said. I don't.
Of electrons.
Where that guy is the number of electrons.
Faraday's constant.
Yeah.
Then standard cell potential times number of moles. They know the number of electrons is a negative.
Yeah, which of actually, yeah, for NF this is negative. But yeah, this is the formula for the Gibbs free energy. So multiply it by the number of moles to give you the maximum work done. Yeah, so the lessons are recorded. So if you still need them, I can still send you the link so that you get to review the topics more at your free time. Okay. Alright, so this morning we want to switch up and basically look at this interesting and very simple topic that is thermochemistry. Yes. What's your question?
Yeah, if the Gibbs energy was negative, yeah, I should ignore the negative sign when finding the same number of the number of electrons.
Finding the number of electrons. What are you talking about? Because
That's being for job.
you're looking at work maximum work done. So usually, if you want, you can put a negative beside. Negative work maximum done is equal to the number of moles multiplied by standards or Gibbs free energy. Now we're saying this guy is negative n effort. It's not like you're looking at electrons to be negative. No, it's part of a formula. You can't get the number of electrons negative. Just put it there as positive, and then it will be negative because of a negative part of the formula.
So meaning that the formula for maximum work is Gibbs free energy times number of moles.
Yes.
So my question.
Okay, can you ask me your questions later? Is that fine?
Yes, sir. It's okay.
Okay, so this morning we want to switch on and just talk about thermochemistry. So under thermochemistry, what we're interested in is we're interested in studying the, each transfer between what we're calling the surroundings and the, if there's the surroundings, then there should be what? Okay, so we have, these are the key terms that we need to deal with. So surroundings, and then we have a system. So we have a system and then a surrounding. So somebody can't see the boards. We can't all see what I'm writing.
Yes, sir.
But all this long, you've just been quiet.
I can see.
Surroundings, system. Okay, so that's what you have. Give an example here. Let's say you have a solution in a beaker. How do you draw a solution? Okay, so this is our solution, right? So we don't know what was reacting, but then, so whatever is inside here is referred to as the system. The beaker is referred to as what? The container. and then everything outside, including the container, is referred to as what? The surroundings. These are very easy terms. These are the terms that we're working with day in, day out, right? Surroundings. So now, as people who are dealing with chemistry, we need to understand that there is what we call exchange between the system and the surroundings. We may have it entering a system, leaving a system. Okay. And not only that, not only do we have exchange in terms of it, we also have exchange in terms of what? Work. Work can be done by the system, or it can be done on what? On the system. Okay, so now the most important thing is for us to be able to identify or know when is it negative and when is it positive. So this guy can be positive, it can also be negative, work can also be positive, and it can also be negative. Okay. I hope we are together.
Yes.
Okay. So we'll start first of all by um, looking at this guy. So people are trying to join in. Let's step in. Yeah. So we said it can also be flowing inside into a system. So what is the system is what is inside there, right? So I'll start first of all by this guy. So when I show that symbol, what does it mean? What kind of a reaction is this where it is being lost to the surroundings? Remember, what is inside there is our system, and then what is outside is what? Surroundings. What kind of a reaction is that? Don't forget your grade 12 work, I'm sure.
Exothermic.
Okay, exothermic. Wow. Okay. Interesting. Okay, people have not forgotten. So we do know what is an exothermic reaction. So now, would you expect the energy of our heat to be negative or positive in an exothermic reaction?
Negative.
Negative. Okay. So we're going to be working with a letter Q to just make things easier under the study of this topic to denote our heat energy. Okay, so that we get to use the same letters that are matching up with everyone else. So heat would denote it's going to be denoted by letter Q. So obviously the opposite is true. The other kind of a reaction is an endothermic reaction, and then we expect our Q to be what? This one we've said is what? It's negative, right? Negative.
Yes.
So in a case where we have gain of heat into a system, or heat flowing into a system, is what? Positive Q, which we are saying is an endothermic reaction. So now, you need to be very careful in every situation that it gets to give you, so that you're able to understand what's going on, right? Because they'll not directly tell you to say it's an endothermic or exothermic, but you need from the context to be able to know what you're given. We understand why it's important to know it's negative and positive. For now, let us know that. Okay, so apart from the heat energy, we also need to understand now a different case that we're dealing with, that is talking about work. So even these things that we're talking about also does perform work. So a system is able to perform work, the surroundings are also able to perform work. So work outside, work in. So whenever work is outside, we say it is done by what? Pay attention, it's done by what? So if you want to think about it in this way, to say it's the system performing work on the surroundings, right? Are we together? Are we on the same page?
Yes.
And then a case where work is in what? How would you put that in simple terms? How do you explain it?
Surrounding is performing work into the system.
Surroundings is performing work into the system. Oh, okay, not bad. Or work is being done on the system. How is that? Work done on what?
So,
On the system. Obviously, it's done by the surroundings as he had put it. Yes?
so you said when work is out of the system, then it's done by the system. That arrow, the red one.
Pardon?
The red arrow.
Yes?
You said you're in, it's indicating that work is coming out.
Yeah, not really coming out, but we are saying it is being done by the system. Yeah. It's only energy that can come out. Right?
Okay.
I hope was fine with everyone. So now, for work, we're going to denote it by the letter itself. Okay. So now, when is it positive and when is it negative? What do you think? What do you think? Hello?
It is positive. Yes, it is positive when work done is when work done on the system is possible, and then it's negative when work is done by the system.
Okay, so this is very easy to tell, right? So whenever things are moving out, or whenever the system is doing work, it's losing energy. Because you realize that from this step, from what we know, we are going to move on and talk about the issue of what? We're going to talk about what we call the internal energy, which is dependent on work and energy. Work and heat energy, of course. So it's very important to understand that for us to determine the energy contained in the system, we need to first of all remove the work that it has done, and then also the energy that it has lost in terms of heat energy. So very important. Thank you for that, sir. So we also have got different kinds of systems that we need to be familiar with, and they can actually ask us to state them. So of course we've said a system is a particular state of substance or a chemical reaction that we focus on in an experiment. So just a particular set. Okay, something that you get to focus on. Particular set of substance. It can be a chemical reaction, it can be a phase change that we focus on. Alright. Very simple. So particular set of substance that we focus on in an experiment, right? To give you an example of a solution. So now we have got different kinds of systems. Of course, the surroundings include everything else outside the system. Are we together? So everything else outside the system is what we are calling the surroundings. So we've got different kinds of systems. We've got what we call an open system, a closed system, and an isolated system. So now pay attention to the differences between these. An open system involves the exchange of the two things that we've talked about, alright? We've talked about work and what? We've talked about work and what? And Q, which is it, right? So a system that is able to exchange these things is what? Is an open system. An example is a beaker. When you have a beaker, you've not covered the top part. You know that the beaker itself has got the ability of losing what? Exchanging it with the surroundings, right? Not so. Are we together?
Yes.
So that kind of a system where there's both, or I can put it this way. Let me just remove work for this, so that we're able to simplify it. So in the case where I've got exchange of heat and matter at the same time, is what we call an open system. So as I've put the beaker there, you find that, for example, if you put boiled water there, right, you find that there's vapor leaving the container, right? Meaning that that is the exchange of matter with the surroundings. And then energy or heat energy is being lost and gained at the same time, right? So that is an example of an open system. In a closed system, let's assume the same beaker, we've covered it. There's no exchange of vapor with the surroundings. But you can still agree with me that even when you've covered the top part, let's assume you've covered it completely with nothing that can allow anything to leave. Like, okay, think of a ball and then you put the what? The lid there. It will not be able to lose any matter. But you find that even when you put hot water or warm water there, it will still be able to cool down, not so. So that tells us to say there's still exchange of what? Heat between the surroundings and the system, but no matter exchange. Very important. And then the isolated one, no exchange of anything. No exchange of heat and matter between the system and the surroundings. So what example can we give under an isolated system? That implies that if you put something there, it will remain as you had put it. Any example of an isolated system?
How about
Pardon?
how about a vacuum flask?
Yeah, that's fine. That's fine. Just a minute. Okay, so we now know the kind of different kinds of systems. So a vacuum flask is an example of an isolated system. So no exchange of matter and what? Heat.
Excuse me, sir.
Yes.
Can you repeat what you said on the closed and isolated system? I didn't understand.
Yeah, so there's exchange of energy here, of course heat energy, between the system and the surroundings. The system, what is inside, and the surroundings, they're able to exchange heat, meaning that if you put, for example, boiled water, it's able to cool down, even without the exchange of vapor with the surroundings. But then for the isolated, there's no matter exchange, meaning that no vapor is lost, and there's also no exchange of what? No exchange of energy, meaning that the liquid is going to be kept, or the solution or a system is going to be kept at a constant temperature. So I'm just using vapor in a case where we have water to just help you understand, but then it's not a necessity that you mention that. So just think of exchange of energy and matter. So where both are being exchanged, it's an open. Where none of them isolated, where only energy and not matter, it's a closed system. Are we together?
Yes, sir.
Yes, sir.
Okay. So now we have what we call now the change in internal energy, right? I'm sure you've seen this symbol somewhere. So that is what we call the internal energy. So what is the internal energy? So this symbol is change of internal energy. Change of internal energy. But what is the internal energy itself? What is it? So we can say our internal energy is just a sum of all the energies of a system. So that is kinetic energy, potential energy. So the sum of all the kinetic and the potential energies for a particle in the system, or for every particle in a system. Or I don't like mastering formulas, so I usually just give you concepts. So internal energy is just a summation of all the energies in a system. That's what you can say. Nothing more, nothing less. So if you add all the kinetic energies and all the potential energies for a system, then that is what we call the internal energy. So then we also need to know, ladies and gentlemen, to say internal energy is referred to as a state function. Very important. Okay. So it's called a state function. So now what is a state function? So a state function is a function dependent only on the present state of a system. It doesn't depend on the pathway by which it got to that state. Okay. So some other examples that can help us understand is when you're talking about, for example, distance. Let me give you an example. Let's say you have a mountain, right? That'd be our example. You do agree with me that from this point A to the top point B, the displacement is the same, right? But do you also agree with me that you can't move straight when you're getting the mountain, right? You're going to find suitable paths to get there, not so. So you may move this way, you go that way. You know, this is the way you can get to that point, not so. That's how you can move, not so. Do you agree? Are you getting me?
You can repeat, sir.
Okay. Do you agree that the distance between
Repeat what you have been saying.
A to B, look at A to B. Don't think too much. Look at A to B.
What's the definition of a function?
Wait. I want you to look at this mountain that we have. If we are told to measure the distance or the displacement between A and B, this is what we've measured, right? So, and do you also agree that it's not possible for you to move straight from A to B? You need to find a suitable path. So you may end up, you move this side until you get to that point B. Not so. How many of you have climbed a mountain?
Yes.
So now what we are saying is the distance between A and B is a state function. It doesn't depend on the path that you've taken. Irrespective of what you've taken, irrespective of the path that you've taken or how you've moved to get to a point B, it doesn't change the distance between A and B. Okay? Are we together? So, while a lot of other things may happen to the system maybe it has lost a lot of energies that gained at different points, that is not going to affect the internal energy. Okay? It is a state function. It is only going to be dependent on the present state at that time. It is only going to be dependent on whatever has happened to a solution does not matter. What matters is only what is present at that time. How much energy is present? Okay. That's what it means. So know that it's a state function. It only depends on the present state of what? Are we together?
Yes.
Okay, so now we're saying this guy.
Don't repeat it.
The problem is he wants to master the formulas or the definitions, that is. What do you want me to repeat? A state function?
Yes, the definition.
You want to write it down? I'll give you the notes. So I said this state function is is dependent only on the present state of the system. That's all. So we are saying now the change in internal energy is equivalent to Q plus what? Plus work. This is our formula. Are we together? Now this formula is going to be changing depending on what we have. So now let's see if you guys are able to interpret this. So I want you to start explaining for me what you can see. So if you talk about the first one there, what is going on there? Change of internal energy is equal to Q plus work. What did you say? What are your comments here? I want to see people are following.
And
Yes? Hello?
endothermic reaction.
Is that all?
And work done by the system.
Work done by the system.
No, on the system.
Okay. The answers are correct, but I'm not satisfied enough where you're coming out. It's like you're doubting.
There, what is happening?
Yes?
There, what is
Yes, we're getting you. What is happening?
happening? The heat is being observed. Then there is being added. So the system, the work is being done. So I think the liquid is leaving the pit.
So you've confused me. So this is it, and this is positive. That tells us to say that what? There was what? Absorption of it or gain of it by a system. And then the fact that work is positive tells us to say that the work was being done on the system. The second one, anyone to help us? What's happening there? You know, these terms are very, yes.
Since our Q, which represents heat, is positive, it means that the system is absorbing heat from the surrounding. But then since the work is negative, it means that the system is the one which is performing the work.
So just the work done by the system. Okay, that's good. The third one, what's happening?
It's the opposite of what I've said.
How is it opposite? Just tell us what's happening there. Work. I want you to be familiar with these terms. That's why I've done this. Work. Work. When work is positive,
Work done on the system, and the system is losing heat.
you know, I gave you this part where you're looking at the aspect of work out. If work is out, it's negative. But there's work can be out, but in the actual sense, we're saying it's a system doing work on the surroundings.
Work done by the surrounding, and
No, don't. And and I don't want you to say. I don't want you to say work done by the surroundings. I want you to say work done on the system. Is it on the system or by the system? Don't use surroundings. Okay. I hope we are together. Then the last one. Work done You're quiet. Work done by what?
Work done by the system.
Work done by the system and what?
Both
What
energy
is
and
the
heat
it
was
means?
lost.
I didn't get you.
No, I think both energy and heat was being lost. Was gained and being lost.
What are you saying? Even wake was being lost. Ah? I refused. I didn't. I didn't say you should use wake. You should say wake lost. No, no, no. Don't use. Don't say that. You can't lose wake.
Work was done by the system.
Yeah. So work done by the system. So we're losing energy as we work outside the system. Okay. So now, good, good, good. Let's talk about expansion and we see what basically
Sir,
happens.
explain on the wake, on the part of the wake, sir. Sir, explain on the part of the wake. I left the meeting.
You watch the recording. So let's talk about expansion here. Pay attention, sir. You understand just from here. So let's assume this is the size of the container initially, and then it gets to expand. It gets to expand. Now I want you to interpret for me. What is it, work done by the system or work done on the system? The container expands in size.
I think work done by the system. On the system.
You're saying you're
Work
contradicting
done by
it.
the system.
Okay.
Work done on the system.
Just explain your answer. How is it work done on the system?
I think work done. There's gain of heat there, so it's work done on the
Who
system.
has talked about the gain of it here?
Expansion.
Hmm? What I'm trying to tell you is I'm not combining these things. Okay? I'm not combining them. I'm talking about each of them separately for certain reasons. So you've seen that the container is expanding there. It has expanded. Is it the work done on the system? Forget about the heat energy.
It's by the system.
It's by the system. Okay. The fact that the system is the one that is affecting the container and the surroundings, it entails us to say that it's for the one working. Okay. So in the case where they tell you to say there was expansion and then they tell you the amount of work involved, just know what you're supposed to add negative there. Okay. And then in a case where we have compression there, the container is becomes smaller. What did you say? Work is what?
Being done in the system.
Okay, work is being done on the system, implying that it's positive, right? Now, for own information, we get to calculate work in terms of pressure and volume as negative pressure, change in what? Change in volume. In a case where we have expansion, ladies and gentlemen, what do we know? When you have expansion from a smaller one to a bigger one, you do know that your what? Your volume 2 is what? Is greater than volume what? Volume 1. So if you subtract volume 2 minus volume 1, it's going to give you what? A positive result, not so? because the other one is bigger, this one is smaller, so it will give you a positive value. So if you have a positive value, it entails to say that your work is what? Negative, because of that negative there. So it is going to be a negative in case of expansion. That's what we said. It's going to be a positive when it's the opposite, because when you're talking about starting with something bigger and then getting to a smaller one, compression there. So what are we trying to say here? We're saying our volume 1 is going to be greater than volume 2, implying that volume 2 minus volume 1 is what? A negative. So if it's a negative, and also in our formula we have a negative, it tells us to say that after multiplying a negative and negative, we have a positive work, which we've said when something is being compressed, when the container is compressed, it implies that work is being done on the system, which tells us to say our work is positive. So the formulas are matching up. So in case they give you constant pressure and then they give you a change in volume,
So yeah,
be able to calculate the work. I have 9 minutes. You've not understood. No, I'm just trying to make it more clear to say. Or if you want to be a lazy student as I used to be, what you'd want to do is just know that when it's expansion, work is what? Expansion, work done by what? The system, negative for expansion. Just know that. And then positive work when it's what? Compression, right? Work is being done on the system. So, and just know that work is equal to pressure times change in volume. So you just want to make sure that when you are dealing with expansion, your work should be negative at the end. Then when it's compression, work should be what? Should be positive at the end. That's all. That's what is important.
So there's no negative in front of the formula.
I've said if you're a lazy student and you don't want to confuse yourself, just know that when it's expansion, at the end of the day, you need to make sure that you get your answer to be positive. Or negative, sorry. I hope that's fine. No one is going to penalize you for a formula.
so
What?
sir, the fixed formula as a negative.
It has a negative. You've already saw. It has a negative. It has a negative. But at the end of the day, I'm just. It is not okay. The formula is not important. What is important is for you to know that expansion is negative. Of course, we've explained that in terms of work being done on the system and by the system. I hope we are together. What is this guy? What do you call him? What do you call? What is enthalpy? What did you say? Hello? What did you say is the enthalpy? I'm sure I've been dealing with this guy for a long period of time now. Okay, so just make things easier. Whenever we're talking about enthalpy, ladies and gentlemen, think of it in terms of what? It's still it. Are we together? The same heat energy that we're talking about is enthalpy. Now, there's one condition that makes it enthalpy. So whenever it is exchanged at constant pressure, it's what? The enthalpy that we're talking about. Are we together? So enthalpy, think of it in terms of what? It's your Q. But whenever you're dealing with pressure, it becomes enthalpy. It's the same. Okay, there's nothing different there. They are one and the same. They're all energies. It's just it that we're talking about. Okay. Are we together? I don't want you to think too much. These things are very simple. So let's go back to our formula. Who can help us with the formula of change in internal energy? What did we say? Change in internal energy is equal to? You forgotten? If you are not able to quote this, if you're not able to remember this formula, then I've wasted my time this morning. What did we say? Summation of what? I'm hoping I've lost my network because no one is responding. Else, I don't know.
Oh, I think I'll leave the meeting.
So most of the people have left the meeting already, right? So let's continue at 14 hours for the sake of the others who've already left. Okay.